Alright, I'm going to do chapter 9 gases on Teach the Doc. So right here I have my formulas of how I converted 450 mmHg to kPa. Right here 101.325 kPa divided by 760 mmHg, 59.9951. And then for torque, 1 mmHg equals 1 torque, so 450. And then I did 450 divided by 760 for ATM equals 0.592. This one right here is Boyle's law, which is what was it, it's supposed to be like what, P over, like P1 over V1 equals P2 over V2. So I divided to isolate P2 equals P1 times V1 over V2. I inputted the values, wrote the values over right here, and then P1 equals 2 ATM. I put it in here, and then since P1 is 2 and it's doubled, it means that P2 is 4. And then for this one, I wrote the values out right here. V1 over N1 equals to V2 over N2. I inputted my values into that. Isolated the V2, which is the value that I want, and then since it's tripled for the N2, I just wrote 3 in front of N1. These crosses out, equals V2 equals 4.5 liters. So I just used the values, input the values from this question, put that in, and that's how I got that. Alright, and then I wrote for ideal gas, I wrote the formula right here, PV equals nRT. I took the values right here. What is it? Pressure is 98.7919 kPa. Temperature is 25 Celsius. Gotta switch that over to Kelvin, which is 298 K. Volume equals 1.5 liters, which you keep that the same. I input it into here. What I'm trying to find is the mole, so the only letter or variable that's remaining is N. Plugged everything in. Isolated the N to be alone. This is right here. Divided over to this side. Moles equals 0.0598 moles. And then let's see, what volume will the gas sample occupy at standard temperature pressure? So I used the same formula as well. So this is my moles, this is my gas constant, which is R, and this is my temperature in kelvins. 1 over here cancels out to equals 1.34 liters. Again, I wrote my values out right here. Let's see, what's the equation that relates to density? So D equals MP over RT. D equals density, P equals pressure, M equals molar mass, temperature is kelvins, and then the gas constant. Let's see, and then what's the molar mass at STP? So I just plugged the values into this formula right here. So density right here gives it right here, 0.901 grams over liters equals M. M is the mass that we're looking for. We just keep that. Pressure is 1 ATM because it's standard. And then my gas constant right here, and then temperature in kelvins. Isolate the M, which equals 20.18 grams moles. Alright, and then second page, let's see. So for this one, I did the gas mixture over the total. So this one is hydrogen H2.5 over 1.47 because that's the total. And I did it for all of the elements. Oh, hydrogen equals 0.34, oxygen equals 0.33, carbon dioxide equals 0.32. So then hydrogen will have the highest torque because it's 0.34. And then for this one, which of the following mixtures exerts the highest total pressure in a 5-liter container? So I just added all of the partial pressures up to get the total. A equals 1.5, B equals 1.4, C equals 1.6, which is why C will have the highest total pressure because it's 1.6. I also wrote that out right here. Add the moles of all elements together to find total pressure of each mixture. And then for this one, I did calculate the mole fraction of each gas. So what I did right here was I did the mass that it gives for hydrogen, which is 3. So 3 over 1 times 1 mole over the mass, the molar mass, equals 1.48 moles of hydrogen. Divide that by the total right here, which equals 0.75. And then I did the same for nitrogen, which is 14 grams. 28.02, because then that's the molar mass, equals 0.5 moles of nitrogen, again divided by the total, which is 1.99 equals 0.25. That's how I got that. All right, and then for calculating the partial pressure of each gas, so what I did was I used this formula, PA equals XA times P total. So what I took was I took the mole fraction of hydrogen, 0.75, times the total right here, which is 1.99, equals 1.47 ATM. And I did the same with nitrogen's values, which is 0.25 times 1.99, which is the total, equals 0.489 ATM. That's how I found it. Okay.